What are solutions? Lecture number 14. So we've talked previously about these making molecules, atoms into molecules, and how these molecules can react in the reactions. And we've mentioned briefly that these pure substances can have three different states: the solid, the liquid, and the gas. And in class the other day we mentioned this aqueous phase. But when we do these reactions, we're involving multiple things in a single, what we call a solution. So a solution is a homogeneous mixture of two or more substances. Right? Typically it's in the same state. So we're taking these homogeneous mixtures, and all of them contain at least two things. Right? We have a solute, which is the substance in the smaller amount, and the solvent, which is the substance in the larger amount. If there's more than two things, then we can have multiple solutes, but only one solvent. So the solvent's always the species that exists in the largest amount. Right? And we always talk about these solutes dissolving into the solvent. Right? So we can have a variety of different solutions in any phase we want. So if we talk about a liquid solution, a common example of that would be like a soft drink, a soda. We can have, the sugar, the carbon dioxide, the coloring. All of that is dissolved in the our solutes that are dissolved in the solvent of water. Right? And we call that this aqueous solution. So all of these solutions that have the solvent of water we refer to as an aqueous solution. Right? We can also talk about a solution in the gas phase. Air, for example, is a good case of a gas phase solution, right? Where the things we have in the smaller amount, this oxygen, argon, methane, water vapor, all of those are smaller amounts within this mixture that is made up primarily of nitrogen. So the nitrogen being the one that's the largest amount is the solvent. We can also, it may seem weird, but we can talk about these solutions in the solid phase, such as brass. Brass is a mixture of zinc in a larger amount of copper. So zinc is the solute, copper is the solvent. So in all of these solutions we have a substance or substances that are in a smaller amount dissolved into this substance with the larger amount. So when we talk about these solutions, we can have one of three things that can happen, and it'll help us distinguish the types of reactions that are possible later. But we can have either can create an electrolyte, a substance that dissolves in water to allow electricity to be conducted, or a non-electrolyte. And it's when it dissolves in water, it doesn't conduct electricity. Right? So we can see at the bottom here, the amount of conduction of electricity is going to give us a various amount of brightness in this bulb. Non-electrolytes, no light. Strong electrolytes, a lot of light. So it's sort of a spectrum. We can have large, strong electrolytes where we conduct a lot of electricity, or non-electrolytes where we conduct very little. So let's look at each one of those in more detail. So these strong electrolytes are something that when dissolved in water, or when they go into water, they break apart completely into their cations and anions. So for example, if we look at the magnesium chloride, when it dissolves in water, we get magnesium 2+ ions and chlorine 1- ions. So we end up with 3 total ions because of the 2 chlorines. But all that exists in that solution is the water molecules and then these ions. The magnesium chloride completely breaks apart in the solution. Right? So we have a large amount of charge in that solution. We're able to conduct a lot of electricity fairly easily. We get a nice bright bulb. If we have a solution or a situation where we dissolve something that doesn't break apart well, such as nitrous acid here, when it breaks into solution, some of it will break apart into the H+ and the NO2-, but some of it will stay together as that nitrous acid compound, the HNO2. Right? So all 3 of these species are present in the solution. Right? So we have a fewer number of ions in that solution, which means we're able to conduct less electricity. So we get some light, but not as much as those strong electrolytes. So we have incomplete dissociation. Strong electrolyte completely dissociates. This weak electrolyte not complete dissociation. So we have all three species, some of that undissolved. For both of these electrolyte solutions, though, the process that allows those separation we talked about a little bit in the class is this process of hydration, where we have the water molecule, where we have this partially positive side and partially negative side of the water. It can interact with those charged either cations or protons, or cations or anions, and the side of the molecule, the water molecule that's partially charged, it's opposite of that sign, will sort of surround those ions. So you can see we have these positives or negatives surrounded by these water molecules. So the water will actually go in between those ions and pull them apart, allowing them to be stable charged species in the solution because they're interacting with the water. And this process is called hydration. We can have a similar process for these non-electrolytes, but the interaction isn't based on their charge. So in these non-electrolytes, we get no dissociation. So if we look at, for example, sugar, when it dissolves in water, C6H12O6, all it does is those individual molecules separate from each other in this mixture of water, but we still have C6H12, now just it's surrounded by water. So we have no ion, these non-electrolytes, we have no ions in solution, therefore we cannot conduct electricity. Right? So basically, if we can break apart these ions, they will, in at least some sense, and that's going to allow us to do a certain type of chemical reaction. If they don't break apart, such as these non-electrolytes, that's going to sort of eliminate some of the potential reactions that we can do, but open up some others. Right? But it'll have a big effect on some of the other properties that we'll talk about later. We can quantify how much a solute is in a solvent using what we call concentration units. So we're going to talk about, I'm going to show you 4 on the slides, but there's a couple more we're going to just talk about that are similar to the ones we'll see. So this concentration is the amount of solute in a given quantity of either solvent or the entire solution. So we're talking about the amount of solute that's present versus everything else. Right? The first one we're going to talk about is this percent by mass. We've already talked about a mass percent before, but now instead of talking about a single molecule, we're talking about this solution. So the percent by mass is the mass of the solute divided by the total mass. Right? So we're taking the mass of that individual solute divided by the mass of the entire solution, the solute plus the solvent, times 100 to make it a percent. Right? We can subdivide that, instead of talking about by multiplying it by 100, we can multiply it by some other factor such as 1,000,000. So in a part per million, it's the same basic setup, the mass of solute divided by mass of the solution, solvent plus the solute, but now we're multiplying by a different factor, in this case 1,000,000. So we call that a ppm, is how many parts of solute per million parts of the solution. We can also talk about part per billion, in which case this number would be multiplied by 10 to the 8th. Part per thousand, again this would be 1,000. So both of these are related in the fact that we're just taking the mass of the solute divided by the total times some factor. 100 for a percent, 1,000,000 if it's a part per million. At the same way, we can take and talk, instead of by mass, we can do by volume. So we can do a percent by volume, which is going to be the volume of the solute divided by the total volume times 100. Or part per million by volume will be the volume of the solute divided by the total volume times 1,000,000. So when we talk about percent by mass, we can also do the corresponding percent by volume. The last set of concentration units, we're going to relate the amount of solute by moles. So in both molarity, capital M, versus molality, lowercase m, the amount of solute that we're talking about is always the moles. So in molarity, capital M, it's moles of solute per liter of solution. So it's the moles per the total volume of the entire solution. In molarity, lowercase m, it's the moles of solute divided by the mass of the solvent, just the solvent, in kilograms. So again, we can talk about these as the quantity of solute in some unit. For both of these, it's moles, divided by some concentration, or some amount, of solution or solvent. Right? Molarity is solution, liters of solution. Molality is mass in kilograms of solvent. So now, using these concentration units, we have an additional way we can talk about amount present. Right? Because all cases we can add it to our idea of stoichiometry. So we have some idea of going from some amount of reactants to some amount of products. Right? If we have a solution, this gives us one additional unit. Right? You'll see for both of these, if we have a volume of some certain concentrations, that'll give us the number of moles. So we can do what we call a dilution, where we transfer a certain amount of moles of solute and then change the amount of solvent, which is going to change the concentration and make it lower. So in a dilution, we're making a lower concentrated solution from a stronger one, or more concentrated, by adding solvent. Right? So, but when we do that, the number of moles of solute we have at the beginning is going to be equal to the moles we have at the end. Right? So if we talk about molarity, where we have moles of solute per liter of solution, if we multiply that volume multiplied by that in 1v1 or MI/VI, that's going to be the number of moles. When we add additional solvent in this dilution, we are still going to have that same number of moles. So that's going to be equal at this side. Right? So in both cases, initially and finally, the number of moles is the same. We're going to take the molarity times the volume has to be equal to the molarity times the volume. Because the number of moles don't change, just the amount of solvent. Right? So this gives us a way we can then calculate, if we do this dilution, we can calculate then concentrations. If we have 2 volumes and 1 molarity, we can calculate the second. Or 2 molarities and 1 volume, we can calculate the new volume. Right? So these are just tools we're going to add in doing this stoichiometry, where now we're talking about an amount of a species, not only in terms of grams or moles, but in this solution type process where we have a concentration. We're going to now add that into our reaction mechanism.
Dad, I didn't get it.